bine. Atunci voi rezolvați acolo problema tehnică. Da, revenim. Domnul Bucataru, bine zic, totuși, vă rugăm pe dumneavoastră să prezentați până facem problemele tehnice de aici. Da, vă ascultăm.
Ok, deci pot să încep eu.
Da, sigur, sigur.
Să dau partajare pentru ecran. Prezentarea este în limba română, așa cum am construit-o pentru concursurile naționale, dar o să încerc să prezint în limba engleză. Să-mi spuneți pentru început dacă se vede.
Da, se vede. Vă ascultăm.
Okay. One moment, please. So, hello everyone. My name is Bucataru Cosmin. I am student in the last year of master at Mathematics and Informatics at Transylvania University of Brussels. My presentation for today is new derivation operators in dual Finsler geometry. For the first part of my talk, I will start with the motivation of my theme. So I'm interested to tell you why I have chosen this type of study, because in the dual Finsler geometry, we want to use two type of coordinates for our Hamiltonian formalism. So we need two notions: the notions of the coordinate of the point and the coordinate of the momenta. And why do we want this? Because we want to use in dual Finsler geometry for the quantum gravity, and this science is in between the connection with the general relativity and quantum mechanics. So we want to study how the small particles move in universe, like photons or atoms or things like that. But when we want to look at these small particles, we don't need the coordinates type like coordinate of the point and the speed that passes through that point. And for this study, we know that we have the tangent bundle, which is studied by Professors Vladimir Ron and Ivan Bucataru. So I want to get more of this study, so I will use the dual formalism, which implies the cotangent bundle. And this is the structure. I want firstly to present you how this thing works in the tangent bundle, study that was presented in the work of Radomir Ron, Ivan Bucataru, Hideo Shimada, and Sabo. And in the second part, I will talk about the cotangent bundle and the dual Finsler structure. And after all, I will present the main results and the future interests of my study. First of all, this is the first thing I want to present is the tangent bundle structure. So M is a manifold, smooth manifold of class C to the power of infinity. N is natural and arbitrary. We denote by Txm the tangent space in the point X of M, and the disjoint union of these tangent spaces we will denote the tangent bundle, and P is the projection on the first factor. And as I said at the motivation, we use two type of coordinates, the coordinates xi and x dot y, which represents the speed through the point x. Then we want to I want to present the notion of nonlinear connection on TM, and for that we need to present the notion of the double tangent bundle, which was introduced by Professor Radomir Ron in 1989. And this another important thing, and then is that for every point x dot, there exists a local natural basis of this type. And what is more important now, on this double tangent bundle, we can make a decomposition. But how can we make this decomposition? Very simple, because we need the projection on a first vector P, but we will take the differentiation, which literally is nothing else than the linear approximation. And this VTM is has the structure of vector space, because when we want to change the coordinates, we only use the Jacobian. But how do we introduce the nonlinear connection concept or the Ehresmann connection, how is alternatively said? The defining term, Ehresmann connection, is defined alternatively by the horizontal subbundle. And we need this decomposition of the double tangent bundle. And why do we need the horizontal decomposition? Because when we want to change the coordinates, this is not a vector space if we keep the same vectors. We need another more component which depends on the nonlinear connection. And with this concept, we can construct the autoparallel curves, and in a simple method, we take a smooth curve on the manifold, and then we lift up. We consider its extension to the tangent bundle, and then we can have the autoparallel curves equation in this relation, where Nij of x dot are the coefficients of the nonlinear connections. Well, we need another concept, the pseudo Finsler space, which is a pair ML, where L is the Lagrangian function defined on a subset of the tangent bundle with two properties: two positive homogeneity in the first one, and the second, the Hessian matrix of the Gij tensor, metric tensor of the manifold. This is non-degenerate, and we will see later why is this important. This construction was introduced also in the paperwork of Bucataru. How do we obtain the geodesics of the pseudo Finsler space? Then this is just gravitational problem, and we return to the notion of the nonlinear connection, because when define that decomposition, I also said that the VTM, so the vertical part decomposition, is naturally induced and is a vector space. So for that part, we don't need to change the vectors, but for the horizontal part, we must take in control of the adapted basis, where we will use the delta I basis vector for the HTM, and this depends on the nonlinear connection. Well, another important property is that for the Lagrangian, we want to be a metric connection. So we have the property that holds in 1.8, that delta IL is 0. And I want to present in the last part of my talk what is the dual structure. Okay. The geodesic deviation the geodesic equations can also be written in the form of 1.10 with the help of the object, the geometric object denoted by the name canonical Sprie, which is nothing more than the vector field around the geodesics, and it has the form in the equation 1.11. What is more important, that we have a proposition that says the integral curves of the lifted C, the C, which are the lifted curve of the C, the small c of the manifold, are the geodesics of the pseudo Finsler space. And then we want more. We want to connect our nonlinear connection, which is canonical, and this is there is only one connection, so the canonical nonlinear connection is unique, we can connect it to the Berval connection, which is linear, through the axioms presented in the 112, where the Berval coefficients are related through the nonlinear coefficients through the formula JKGA is partial derivative of n coefficients over the speed through the point. And with this notion, we can introduce the notion of the dynamical covariant derivative, which measures the variations of the speed through the geodesics. And then, with the help of this operator, we can use an elegant form, like in the proposition 1.2. So nabla c dot equals to 0. And this was the introduction part. Now I will skip some details of the demonstrations, just the important stuff I want to present. So I want to present the notion of the cotangent bundle, which where the difference is that we use with the cotangent space denoted by Tx star m, and the T star m is the disjoint union of these cotangent spaces. And the big difference is that when we use the local coordinates, they're naturally induced by the coordinates of m, but the second coordinates are the momenta, not the speed. In the same way, we can introduce a nonlinear connection Eresman, and this is the new concept where we denote it by n star. And the decomposition is the Whitney sum between the horizontal subbundle of the cotangent bundle and the vertical subbundle of the cotangent bundle. Okay, in the same manner, now we can introduce the adapted basis to for the T star m for the cotangent bundle, but in the relation 2.2, we will see that NJI coefficients are we have all the both indices ups down star, because when we use the momenta, the indices must be down. Okay. This is how the adapted basis will change over the double cotangent bundle. And the most important thing that we will use in the next session is that we want the invariance to the change of coordinates. And then, of course, the auto-parallel of the nonlinear connections take the form in the equation 2.8. So now we will use a concept introduced by Professor Arnold, which is the Legendre transform that connects the Hamiltonian with the Lagrangian. And another thing is that the geodesics of the dual space M hash, which we will introduce in the next slide, the Legendre transformation of the geodesics of AL are exactly the geodesics of the dual Finsler space. It means that the solution curves are the equations of the Hamilton equations, which are related in the
Mai aveți 2 minute.
2.10. Okay, a dual Finsler space is also pair MH, where H is defined on a subset of the cotangent bundle. It also have the two homogeneity property, and also the Hessian matrix is non-degenerate. But another important detail I want to show you, why can we use the Legendre transform and why it is bijective? Because we started with a Lagrangian, which Hessian is a non-degenerate. So this is the reason why we can use this notion of the Legendre transform. Well, in order to have the duality, we must introduce this property. So H, our Hamiltonian, must be a metric connection. So delta E star H needs to be 0. And I will show you where this condition is important. Then,
să încercați să vă încadrați într-un minut, vă rog.
Yes, I don't have, I don't need very much time. This is how it is defined the Hamiltonian vector field, which will be the dual notion of the geodesic Sprie. And this is the proposition, original result which is the joint work with my coordinator of Nicoleta Voicu. And these conditions are equivalent. We wanted to show that if C star is the integral curve, then the properties 2 and 3 are also equivalent. And another two results, theorem 2.1, we wanted to show that the XH, so the Hamiltonian vector field, is the dual notion of the canonical Sprie. So we obtained this relation in the theorem 2.1, where it was very absolutely necessary to use the definition introduced. So the H must be a metric connection. In the same manner, we can connect linear connection, which is the Berval connection associated with the N star nonlinear connection. We introduce two notations, key star V and key star H, for which denote the vertical vector fields and horizontal vector fields. And with these notions, we will introduce the new operator Nabla star, which can be seen in the relations 3.5 and 3.6. And with this new operator, we demonstrated that Nabla star checkpoint star equals to 0. So this is the main theorem of our study. And other important results that we obtain after is that Nabla star G star equals to 0 and Nabla star H equals to 0. And in order to show how this concept works, because it's a very abstract notion, I have here an example of the tangent bundle construction of one-dimensional manifold. And if I have 30 seconds more, I want to show you how this works. I just made an application by myself using the soft Desmos, and this is how it works. So this is the personal example where we can see how the tangent bundle is related to a manifold. And the futures in future, I'm
thank you very much.
This is my biography, and thank you for the attention.
Și noi vă mulțumim foarte mult. O prezentare foarte frumoasă.